So welcome back. I hope you remember stuff before midsem. So what were you discussing before midsem? Just the last topic before midsem. Right. Yeah. Yeah. Thank you. So let's start off from there. So looks like you guys are familiar with this structure now. So there is a sorry, this was one of the midsem questions, right? So there is a nomenclature for this structure. This structure is called common source amplifier. I'll qualify why it is called shortly. CSM. So it is called common source because if you look at the incremental picture, what does the incremental picture looks like? It essentially means that the input is connected to the gate, between the gate and the source, kind of. If this is the drain, so this source is grounded. This is Y21 times VSG, and we're taking the output here, right? This is the drain. This is essentially the drain. This is the source. And direction of the current? Source to drain. So as you see that this terminology, VSG, what does this mean? This means you are applied a voltage between the way you have applied the voltage has been applied between the source and the gate, and the source is common to the drain. I mean, the way you are taking the output, you are essentially taking the output between drain and ground, and while the input is applied between gate and ground incrementally, isn't it? So the ground is here. So the source is grounded. Effectively, you can say that the input has been applied between the gate and the ground, and you are taking the output between the drain and the ground. Right? So in other words, this is almost like a grounded source amplifier, right? So it's not necessary that a source should always be grounded. I mean, we saw in some of the assignment problems also there was a question in itself that source need not be grounded all the time. So this is a particular case where the source is incrementally grounded. So whenever an amplifier topology has an incrementally grounded source, it's termed a common source amplifier. You will see that this type of nomenclature will be a regular occurrence. Whenever we say common source, common essentially means in the incremental domain, it is grounded. Okay. Later on, you will see that you will have common gate, common drain amplifiers. Those terms will come, and at that time, that should make sense because you will see that in some cases you will have drain to be incrementally grounded. In some cases, you are going to have gate to be incrementally grounded. But it's good to know how the nomenclatures came into being. Okay. So now the stuff that we were discussing before the midsem was this floating battery stuff is not acceptable. So if floating battery is not acceptable for a practical usage, what can we do? We saw that a capacitor, an infinitely large capacitor, can behave almost like a battery because you can keep on pulling charges out of it and the voltage across it won't change, right? So it's almost it's infinitely large capacitor is a battery. Now, practical problem is how do we get infinite capacitor? We cannot get infinitely large capacitor. So what is the workaround? The workaround is to see if we can use a finite value capacitor, mimic the performance of a infinitely large capacitor, right? So let's see. So let's say let's take some values. VDD 5 volt. I want this battery to be 2 volt. Okay. So let's try first biasing the circuit. Let's forget about this guy. Okay. So, and I want to, given the fact that I have one single battery, because that's what we started off with, we need to bias everything with one single battery. We have a 5 volt battery. We have a 5 volt battery. and I have a capacitor which needs to be charged to 2 volt. So what should I do? Voltage divider, right? Great. So let's put a voltage divider. So let's put a voltage divider here. So let's call it R2, R1. So what relationship do you want between R1 and R2 to get 2 volts here? Yeah, so the ratio has to be R1 by R1 plus R2 has to be equal to 2 by 5. Let's take some values. Maybe this is 2K, this is 3K. Okay, so I connect it here, this becomes 2 volt. Okay, so far so good. This becomes the battery, but now this becomes a capacitor charged to 2 volt. Now, how do I get now the next question comes is how do I connect the input and how do I connect this capacitor to the gate of our amplifier, right? We know that we have this. So somehow I have to connect this to that. How do I go about doing it?
So we can make this a VDD. VDD is also 5 volt.
Oh, yeah. So this is agreed. This maybe I can connect it up. So this connects here. So this VDD is connected. Is also connected. So now what voltage does this require? 2 volt. Where from can I get 2 volt?
Directly connect with capacitor.
Yeah, let's directly connect. That's the most obvious thing to do. So let's directly connect the capacitor. Just because I'm asking the question doesn't mean you cannot. You can always. So, okay. So now what about the input? So I have another input, isn't it? So I have an input. So what should I do about it? The input also has an RS. Generally, it has an RS. We didn't use the RS earlier because it was going into a gate. It was not loading and anything. But generally, we have an RS. So how should I connect this?
Below the.
Yeah, so if I just look at this scenario, so here earlier, what was the scenario? Earlier, so essentially, what are you trying to do? We are trying to mimic this battery using a capacitor. So the higher end of the battery has been connected here. In this case, the lower end was being connected to the ground. And if I apply a signal source, the lower terminal, the negative terminal of the capacitor was getting applied to the signal source, right? So we can try doing the same thing. So let's do the same thing here. Okay, so let's connect all the grounds together. Okay. So now the question is this topology identical to the topology using a battery, right? So this is an example of how you go about designing something, and then you'll have to figure out whether the stuff that you have designed is actually what you want. So there the analysis will help. Right? So you have to do an analysis on this to figure out whether this topology, behaves like the case where we didn't have the capacitor, but we had the battery. Okay. So if we have to do that, what should we look for? Do you understand the question? Right. So essentially the question is, I am trying to replace this battery using this contraption. So not only this entire contraption. Yes. Okay, so good question. So his question is, we are getting VDD here directly, so why not connect the voltage source directly? So let me do one thing. Let me get rid of the RS first, because RS probably overcomplicates things. So let's do this. This is what you mean? Okay, fine, great. So do you see any issue with this, or this is fine?
VG will always need to be.
Yeah, VG will always be equal to VI. Oscillating is not a very bad thing, right? Ultimately, your input is oscillation. I mean, input is a sinusoidal waveform that's what you want. But there is a problem here is that this is a zero mean signal, right? Generally, it's a sinusoid, which is zero mean signal. Zero mean signal means is DC quiescent is zero, isn't it? But you want quiescent to be here to be 2 volt. So you have to lift the quiescent. So the battery was lifting the quiescent earlier. Now we don't have the battery, it will not be able to lift. So we are putting the capacitor to lift the quiescent. Yes.
VI to the wire the
Resistance.
You wanted to connect the VI where? Here? Okay, understood. Very good question. So question is, why not connect VI here? If you can do this, this is going to work. The problem is you cannot have a floating source. So when you are doing this, what you are essentially saying is, so if you think of 2 cases, the cases that you will be familiar with is ESC201 lab when you have a single source. You have this big box. So only one side of the box gives you the signal, other side is internally grounded. So all the sources that you are, regardless of whether it's a power supply or a signal source, one side has to be incrementally grounded. That's a practical consideration. The other problem is, let's say this signal source is not a pristine source that you are pulling from a box. It's probably the previous stage amplifier output. For example, let's say this is this. And this has to go into the gate of the second stage. Then you cannot obviously put this voltage in series, isn't it? Because you have access to only one terminal. And this is more of a practical problem also, because normally you always use multiple amplifiers, one cascaded with another, then you cannot do that. So this, even though seems like a very nice solution, but the issue is it's a practical problem. You cannot use floating sources.
So
yes.
In the previous part, where you had drawn, where we had moved the capacitor, I still couldn't get why can't we remove it, because if it's directly connected there also.
This one?
Yes.
Okay. So when I connect like this 2K, 3K are irrelevant, right?
Why, sir, they'll set the voltage there.
No, okay. So what is the voltage here? So let's say VI is equal to VP sine omega t. So what is the voltage here? This is VP sine omega t.
But how it's violating some law then. Okay,
What law?
The single point part have different voltages.
Okay, so good question. So let's. So yeah, exactly that, right? So what is this? This is this. So what will be the voltage at this?
Got it.
Do you understand? No? Okay. So let me draw it like this. Okay. What will be the voltage at this node? Yeah, this one. This will be provided as a source, right? So why is it different if I connect something like this here? Right? So I understand your problem. The way this seems a bit different, because it seems like initially the way I led up to the problem is this voltage was being set by this VDD. Then I connected it here. Why is that voltage changing? That voltage is changing because ultimately it doesn't matter if you have a battery or a source and you connect any load across it. So it will always be that source voltage because it's an ideal source, at least on a piece of paper, right? Okay. So now the question is, let me ask you the question in another way. So what needs to change for this voltage to go to Vp sin omega t? So essentially, initially when this was not connected, this voltage was 2 volt. And when I connect this voltage changes. Why does it change? Flow of current. Now the current path was initially through this. Correct? From top to bottom and through the R1, R2 resistor. But now moment I connect this, the current path can be this. Right? So essentially the current path changes and that's another way of saying that the voltage that you were trying to observe has changed. Okay, great. So now if we understand, if you're okay with this fact that we need something here, so that let's proceed. Fine. So now at least intuitively it seems like this might work, but we are still not sure. So let's do an analysis. So what I would like to do is say that this is a voltage source of sinusoidal voltage source operating at frequency omega. I want to find out what will be the voltage at this node when both, I mean, under the condition that you see on the screen right now. So now, can you tell me whether the existence of this device will affect that voltage? No, right? So basically that voltage is out of the equation. So now we'll have to find out what will be the voltage at this node. So what should I do to figure out what is the voltage at that node? Steady state, sinusoidal steady state analysis. So what I can simply do, go into the phasor domain and find out what will the voltage at that node, right? So if I have to find out the phasor, if I have to do a phasor analysis, what needs to change? What should I replace here? Yeah, so the capacitor gets replaced with its phasor equivalent impedance, which is 1 by j omega naught c. So let me replace that. So this is 1 by j omega naught c. Again, what does this omega naught represent? Which frequency? Yeah, it's not necessarily the fundamental frequency, it's the frequency of the source. If the source has multiple frequencies, then the capacitor will also give you multiple impedances. Okay, so now can you quickly do a calculation and tell me in the phasor domain what will be this voltage Vg? I'll call it Vg j omega naught because we are doing phasor analysis. Okay, so tell me what you get. So let's keep it in the form of R1, R2, so keep it general. So what will I get? So Vg j omega naught. So firstly, there are two sources. One is VDD, one is VI. Both of them are operating at different frequencies. So I'll have essentially, firstly, phasor analysis, is it a linear or a non-linear analysis? Linear. So I can use superposition, right? So this boils down to the question that the comment that he just made. You have two sources operating at different frequencies. Vi operating at omega naught, VDD operating at 0. So the capacitor will give different impedance to both the sources at both the frequencies, right? When it's operating at omega naught, I'll have 1 over j omega naught c to be the impedance of the capacitor. When I'm operating at VDD or 0, the capacitor will behave like a open circuit, right? So I'll write two equations, superposition, add them up, right? So when I am talking about, when I'm essentially saying what is Vg, when I'm saying Vg j omega naught, essentially what I'm essentially saying is I'm doing the analysis under the assumption that there is only one source which is operating at omega naught. In that case, what will be the output? The output will simply be the equivalent of whatever we see. I can redraw. Let me redraw for us. That will make more sense. So we have this. This is R2. And the other guy here, R1. What should I do to the others, to VDD? Short. So essentially this becomes R1 parallel R2. So this is 1 by j omega naught C. So Vg j omega or j omega naught becomes Vi R1 parallel R2 by R1 parallel R2 plus 1 by j omega naught C. Right? Make sense? So does it make sense? Okay, fine. Okay, so this is with when we have when there is only one input at frequency omega naught, but we have two inputs. The other input is at VDD. So if I have to find out Vg for a frequency of 0, in this case, in this particular topology, what will I get? So when I am doing this, what are we essentially saying? We are saying we are doing one at a time, right? We are using superposition. So in the earlier case, we grounded VDD. In this case, we are going to ground Vi and then find out that voltage at the gate. What will be that voltage? Yeah. VDD R1 by R1 plus R2. Superposition means now we'll have to add both of them up to get the final voltage, total voltage, right? So VG, this is total, will be VG0 plus VG at the frequency. I should not write it in this format because sometimes it gives the impression that inputs have been applied at the same position, but which is not really true. So this is Vi R1 parallel R2. So this gives you that 2 volt, right? The way we biased it initially, this gives you the 2 volt, and this gives you some factor of the input, right? So ideally, this should have been the input, right? Had this been an ideal battery, then your output should have been this 2 volt plus the input. But it's not an ideal battery. It's a capacitor. So output is 2 volt plus some fraction of the input. Okay. So if we want this fraction to be as close to Vi as possible, so what design choice will you make? So yeah, so the if for ideal battery, your Vg total should have been Vi plus this 2 volt, right? So let me go back to this picture. This Vg should have been Vi plus 2 volt. Now this is, I get this 2 volt, but I don't get Vi. I get a fraction of Vi or some complex form of Vi. In phasor, complex means essentially there is a phase difference between the input and whatever you are taking the output. So now is it clear? Okay. So now the question is, I want, as a designer, I want to make sure this is as close to Vi as possible. Yeah, increase the value of the capacitance. You see that if C goes to infinity, naturally we satisfy that condition that we are initially after. So at least the sanity check holds. So now the question is, we cannot get infinity, but then it looks like we have a choice of the capacitor. If we can find out a range of values of capacitor for which this becomes almost equal to Vi, then we are all good. Then for all practical purposes, the capacitor acts as a battery. So what is the condition? The condition is R1 parallel R2 should be much greater than 1 by omega C. Or in other words, C times R1 parallel R2 much greater than 1 by omega naught. So now you see that this R1, R2 and capacitor values are all design choices. We can choose the values as we please. So if we can choose the value as we please, then obviously then looks like even without a floating battery, we can manufacture a condition where our RC, where they're using a capacitor and a set of resistors, we can arrange our sources and the contraptions in such a way that it almost behaves like a floating battery. But there is a catch. The catch is you cannot have this for a non-zero frequency. Or sorry, you cannot have this for a zero frequency. It has to be for a non-zero frequency always. Because if omega naught goes to zero, then this is not going to work. Okay. So that is the only catch. As long as the input is a sinusoidal, or as long as the input is changing with respect to time, then there is a way of putting a capacitor, using a capacitor in the way that we have shown, and making it behave like a battery. Make sense?
So,
yes.
Suppose this fraction becomes equal to 1/2. Then, and if we want the output to be VI, then we can just choose a battery which has double the requirements. If the fraction is 1/2 and we want it to be a 2-volt 2 sine omega t source, then what we can do is we can take a battery of 4 sine omega t and
exactly. What he is pointing out is, if let's say, I mean, for whatever reason I was not able to choose R1, R2 and C in such a way that this is not as close to 1 as possible, right? So let's say for whatever reason it becomes half, then basically the mod of, you have to take the magnitude of it, right? R1 parallel R2 by under root this square plus that square, you do, and you find out the magnitude, and you find out that this whatever the magnitude of this is equal to 1/2. Then it makes sense to say that at the input I will not drive by Vp sine omega naught t, I'll drive by 2 Vp sine omega naught t. Perfectly fine, as long as you have that 2 Vp sine omega naught t, right? So our purpose is we are trying to generate a 2 Vp sine omega naught t. If we had it in the first place, then why bother? But I mean, whatever you said, sometimes that is also done for some other context, not for amplification purposes, but some other context that is also done. Okay, fine. So, now I did all this bunch of math, but there are a couple of other ways of approaching this. So one of the ways, what I would like you to appreciate is, this is the way we approached is how a designer would approach the scenario, given that we are starting from scratch. If we are not starting from scratch and we know that something like this exists, then how should we go about thinking about it, right? So in other words, what I'm saying is, so let's say I know this circuit. Now that we have designed this, I know this exists. So how should I go about thinking about it, right? So it's almost like you are exposed to something for the first time. It's novel, but then you do it a couple of times, then you would like to see how quickly I can get about finding out the values. So the way to think about it is as follows. So for example, in a very crude term, I can say that the purpose of this capacitor here is serving two purposes. One purpose is, it's not allowing the quiescent voltage here to change, which is getting set by the VDD and R1 and R2, because the capacitor is giving me infinite impedance at DC. So it's not troubling the quiescent voltage. If I connected VI directly to that node, then the quiescent voltage would have been disturbed. So the capacitor is blocking the DC. So this is often called a DC blocking capacitor, if you use it in this format. You will hear this nomenclature if you look into literature. But I mean, just if somebody suddenly comes up and tells you that use a DC blocking capacitor, just don't get phased about it. This is what it means. The second purpose the capacitor is serving is whatever it is serving is, if you see that if I want this VI to appear directly as a VI across that node, which means the capacitor is acting like a short circuit to a non-zero frequency signal. Right? So it's serving two purposes. One is serving the purpose of setting the quiescent or not disturbing the quiescent by giving infinite impedance to a DC signal. And it's serving the purpose of transmitting the VI across it without any attenuation, which means it's giving zero impedance to a non-zero frequency signal. Okay. So now nothing can be zero, right? So it has to be something. I mean, it has to be some approximation. So which essentially means that this will not be Vi, this will be approximately equal to Vi. And that's what we saw here also, right? So this expression, I mean, magnitude of the expression cannot ever be equal to Vi. It will be less than Vi, but approximately equal to Vi. So now the question that a designer would ask is that, then what value of the capacitor should I choose so that it behaves almost like a short circuit, right? At omega naught. So VDD doesn't matter anymore because capacitor gives you infinite impedance anyway to all DC. So I can as well say that that doesn't exist for our analysis. All we are doing is to figure out, we have this impedance 1 by j omega naught C. The question that we are asking is, for what values of capacitance this looks like a short circuit? So whenever we say something looks like a short circuit, what we essentially mean is it's looking like a short circuit with respect to what? It's not never absolutely zero, right? It will be small with respect to something. What should it be small with respect to? Pardon? Yeah, so the question I'm asking is that the impedance of one of this is 1 over j, but magnitude of 1 over j omega naught C should be small with respect to what? R1 parallel R2, right? Because I mean, this is essentially this, right? R1. So as long as we can ensure that 1 over omega naught C is much less than R1 parallel R2, so this voltage will be equal to, approximately equal to Vi, right? So you see, this is essentially that condition. Okay. So once you know the design, the way you go about choosing value is arguing in this manner as to what do you want to do. In order to get to what you want to do, you do impose the condition. And more often than not, you will see that it will come to you very easily, as long as you know exactly what you want. If you don't know what you want, then nothing will come. Doesn't matter. Okay, so there is another way of thinking about this, and that is as follows. Have you heard of this thing called time constants? Right. So what does this? What do you understand by time constants? Let me rephrase. If I say a circuit has large time constant, what does it mean? Pardon? Capacitor voltage decreases slowly, right? So in this case, when I am choosing a value of the capacitor for in this our particular application, do you want the time constant of the capacitor to be very large, very small? Very large, right? Why? So that it voltage. Yeah, voltage across the capacitor should be 2 volt all the time, right? So essentially what we are saying is that the voltage across the capacitor should not change at all, isn't it? So, okay, some of you look a bit confused. So let me address this once again. So ideally, let's say capacitor value is infinite, R1, R2 infinite and everything. What should be the voltage across this capacitor? This was 2K, this is 3K, 5 volt. Across the capacitor, how much will be the voltage ideally? Expected value? 2 volt, right? Because the capacitor is mimicking a battery of 2 volt. That's what we wanted, right? So when the input changes, goes up and down, do you expect that 2 volt to change across the battery? No. So you don't expect the capacitor voltage to change, right? Make sense? So now in a first order circuit, by the way, time constant and all these things are valid only for first order circuits. Okay, so this is a first order circuit or a second order circuit or third order circuit? First order. How do you know? Great. One capacitor, effectively one resistor, first order circuit. So in a first order circuit, what will be the time constant in this case? What will C is C? What will be R? R1 parallel R2. So we say that time constant has to be really large, which means it has to be much greater than something. Correct? So what is that something? Because when the time constant things are always, we say time, all the analysis of time constant are done for like step inputs, right? Which the change happens once and it goes on forever. Typically, that's what time constant means, right? You apply a step and you see how slowly or how quickly the step settles, 1 by E of its final value, and so on. That's how time constant came, isn't it? So the input that we are, whenever we are talking about time constant, at the back of your mind, you are essentially saying the kind of input we are dealing with is a step input. Correct? But here we don't have a step input. This is a sinusoidal input. But time constant relates to some sort of change. As you rightly pointed out, when you have large time constant, which means the voltage across the capacitor does not change. It changes very slowly. So what is the time scale that we are talking of here? One time period of the input. Correct? So essentially, I mean, if we don't do any analysis, all we have to say is that as long as this time constant is much, much greater than one time period, T naught, then we are good. T naught is essentially 1 by F naught. As long as this is fine, then this contraption should look like whatever we want, right? So what I'm trying to get at is that sometimes in circuits, it's not very straightforward to do analysis of the full circuit all the time. It's sometimes easier to break down the circuit into smaller pieces of first order circuits. Now we are good at analyzing first order circuits. One of the guiding parameters for a first order circuit is a time constant. So if you can relate something to a time constant, then analysis becomes easy, right? So I'm trying to relate the time, whatever you have done with the time constant of a first order circuit. So in this case, as long as this condition is valid, then we are good. But you see that this is not exactly what we got. We got with respect to omega naught, right? So as it turns out, that extra 2 pi that you get, I mean, that's just one of those, I mean, if you do the brute force mathematics, that the 2 pi will come. But as long as we get the approximate idea, or we get the idea of what the approximations are supposed to be, and it's fine. Okay. So don't get bothered about why this doesn't have 2 pi. I mean, ideally, the way I have gone ahead, this should be 2 pi over omega naught. Right? So the approximation should be this, isn't it? So the approximation should be this, but I mean, what I am essentially, my comment to you is that don't get bothered with this 2 pi thing, because it's just one of those things that comes when you extrapolate an intuition too much, right? So it never matches fully. So if you do the full analysis, this is what the conditions are. But the intuition behind why time constant relates to a case where you have sinusoidal input is whatever I told you. So the period that we are talking about is one cycle of the one cycle of your sinusoid, and as long as the capacitor is able to hold its DC value without much change, because it is going to change. If the capacitor is able to hold the DC value without much change across the full cycle of an input, it behaves like a short circuit, right? So what is the moral of the story? The crux of the matter is a capacitor with a large time constant can behave like a short circuit for a AC input, as long as you satisfy the condition that RC, the equivalent R times C, is much, much greater than 1 over omega naught, right? So that essentially is a takeaway from this lecture. Okay, so now an extrapolation of this is, let's say you have a very big circuit which has all R's and let's say 1C and many control sources and so on. So what I can do is, let's say I have a big network N which has control sources, R's, and whatever. I mean, all 4 types of control sources that you know, but it has only one capacitor. And I take the capacitor out. And maybe there is a voltage source somewhere. I want to ensure that this capacitor, this voltage source is at omega naught. I mean, this signal frequency is at omega naught. I want to ensure this capacitor behaves like a short circuit when I put this capacitor in the way I have shown. So what is it that you are going to check? Yeah, you are going to check the time constant. How are you going to find out the time constant?
By finding the R.
You have to find out the R Thevenin. Effectively, you have to find out the equivalent resistance or ROC or R Thevenin or R equivalent, however you want to call it, all are same. So you find out the resistance. In order to find out the resistance, you'll have to short these inputs. And the same thing that we have been doing for Nortons and Thevenins all the way. And whatever equivalent you get, multiply that R with capacitor, you get the time constant. Then you set the condition that time constant has to be much, much greater than 1 over omega naught, and you're good. Okay. So last thing before we leave. So this is the condition where we want the capacitor to behave like a short circuit. If we want the capacitor to behave like an open circuit for certain frequency omega naught, what should be the condition? Sign should be reversed, essentially, right? So RC time constant should be much, much lesser than 1 over omega naught. You will see later on that in some cases we will be faced with such conditions where we want the capacitor to behave like an open circuit, and that in those cases this will come in handy. We'll just find out the time constant, right? Because we are good in finding time constant of first order circuits. We find out the time constant and assume that it's all. I mean, as long as we know time constant, we relate it to 1 over omega naught. If we do it. And the signs are right, that is, you don't mess up greater than with less than, you're good. Okay. Any questions? Okay. So before we end, have you guys done, I'm sure you have, do you remember, should be the right question, phasor analysis by plotting magnitude and phase responses? Okay, fine, great. So we'll start off maybe with that in the next class.